Welcome to the next session. Today we will be continuing our discussion on chapter 4, which is the topic of sampling. And if you look at the overall plan, the topics for week 1 and 2, which is the introduction and review of discrete time signals and discrete time systems, have been completed, and we are now discussing the topic of sampling, and we'd like to build on that. For the corresponding reading, I would encourage you to look at Oppenheim and Schaefer chapter 4. The chapter heading is Sampling of Continuous Time Signals. Correspondingly, in the book reference book by Rawat, it is in chapter 2, which is titled Sampling and Quantization. Very broadly, we explained that sampling is the process by which we go from continuous time to discrete time. So that is an important capability which helps us transform from continuous time processing of signals to discrete time processing of signals. Once you move it into the discrete time, we're able to leverage a number of advantages of being in the discrete time. One of the main advantages is the ability to use the signal processing tools as well as the computing power that we have. So we will study a little bit more about that as we move along. So what are some of the topics that we have covered in the last class? Let me just quickly capture them for you. We looked at the various interconnections of LTI systems. You could look at a cascade of two LTI systems. The main result is that when you have LTI systems, you can put them in any order. You can interchange the order in which the cascade is implemented. So H1 of n followed by H2 of n, two LTI systems, is the same as the input being operated upon by H2 of n first followed by H1 of n. Similarly, if you have two LTI systems which are in a parallel connection, it is the same as having an equivalent LTI system which is equal to the sum of the two impulse responses. So in this manner, we are able to not only find good ways of implementing LTI systems, but we also have a way of simplifying LTI systems, and so these results are very helpful for us in the context of working with LTI systems. Then there were a number of results with respect to the properties of LTI systems. Let me just summarize them for you. An LTI system is said to be causal if its impulse response is causal. So LTI system is characterized by the impulse response h of n. The LTI system is causal if h of n is causal. Similarly, an LTI system is bibostable if the impulse response is absolutely summable. Then we define the energy of a sequence, the power of a sequence, what is the power of periodic signals, and then we also said that if you have a periodic signal, then we will have a finite power, but the energy will be infinity. On the other hand, if you have finite energy signal, the energy will be finite and the power will be zero. These are called energy signals. So this is some terminology that we had introduced last time. And we had just introduced the concept of the discrete time Fourier transform, or also known as DTFT. Now this is a very powerful tool which we will be covering in detail. But at this point, let me just mention that the transform is given in the form as, if you have a discrete time sequence x of n, the corresponding Fourier transform, which is given by x e of j omega, is given by a summation n equal to minus infinity to infinity x of n e power minus j omega n. And similarly, there is an inverse transformation. We will be studying this in more detail. So for now, we will just take it as a Fourier transform pair. Any discrete time signal can be represented by means of its discrete time Fourier transform, and we can go back from the discrete time Fourier transform back to the discrete time domain. One important observation that we make even at this stage, if you look at x e of j omega, now the discrete time Fourier transform is a function of omega. Now we know that omega, if you replace with omega plus 2 pi, everything will repeat, because in discrete time frequency there is an inherent periodicity with multiples of 2 pi. So the discrete time Fourier transform of any discrete time sequence will be a periodic signal, and its period will be equal to 2 pi, and that property will come into play even in today's discussion. But again, this is a transform technique. This is very powerful, which we will be looking at in detail in the next session. So let us move forward. In the last lecture, we introduced the notion of Nyquist sampling theorem, We said that if xc of t, a continuous time signal, is band limited. What do we mean by band limited? If you look at the Fourier transform, which is given in the top right hand corner, if the spectrum of the signal is limited to minus omega n to omega n, we say that this signal is band limited. In such a situation, the band limited signal can be sampled and represented by means of a discrete time sequence and eventually converted back to the continuous time signal, provided we satisfy the Nyquist rate. And the Nyquist rate says that the sampling rate of the conversion process must be at least as high as 2 times the highest frequency component of the continuous time signal. So, in other words, if omega n is the highest frequency component, the Nyquist sampling rate is 2 times omega n, and any sampling frequency which is higher than the Nyquist rate is also good enough for us to be able to reconstruct the original signal. However, if you go below the Nyquist rate, then we will find that we will not satisfy the basic requirement and we will not be able to recover the original signal. Now, one point to note is that the way we represent the conversion from continuous time to discrete time is by saying that the continuous time signal xc of t is fed into a C to D converter. We have not yet described what is inside that box. We will study that in today. We will specify a sampling period Ts, and output will come a sequence of numbers in discrete time whose value will be equal to the continuous time signal at those time instances. Now, if assume that you have 2 sampling periods, one is Ts, which satisfies the Nyquist rate. So, let us say that this is one of our, and we sample the discrete time signal and we have obtained these points. So, it has satisfied the Nyquist criterion. So, therefore, we are able to get the required number of samples. Now, if I were to reduce or increase the sampling rate by a factor of 2, in other words, the sampling period will become 1/2 of that. If the sampling period here is 2t1, here the sampling period is t1. And you can notice that the grid that appears is now much more dense because you are sampling at twice the rate. Now, both of these systems, both of these scenarios, if we satisfy the Nyquist criterion, then we can reconstruct it. However, in the case where you have the higher sampling frequency, then we are able to do a more effective reconstruction. But the basic underlying principle is that there is a Nyquist criterion which we must always be aware of and also satisfy that, so that we can then convert from the discrete time back to the continuous time. We also mentioned that there are some properties of the Dirac delta which we would like to capture, and that we have mentioned. The Dirac delta is a function which is undefined everywhere except at t equal to 0, is equal to 0 everywhere else, and at t equal to 0 its height goes to infinity. So, basically there is the only way to define the Dirac delta is through the 2 properties that are listed below. Integral minus infinity to infinity delta of tau d tau is equal to 1, and minus infinity to infinity x of tau d tau delta of tau d tau is equal to x of 0. Now, there is also 2 more properties which I would like to highlight for you, which are useful for us, which will serve as a reference. Now, if I have a continuous time signal x of t and I multiply it by delta of t minus t naught, what do I get? Now, remember, delta of t, the delta function now is going to occur at t equal to t naught, and it is 0 everywhere else. So, the x of t, though it may have non-zero values everywhere, the only value that will be retained will be x of t naught, and not only will it have only at that point, it will have the property of the Dirac delta. So, it is a Dirac delta occurring at t equal to t naught with a scale function x of t naught. So, this is an important element that we need to keep in mind. Now, if you look at minus infinity to infinity, if you integrate this particular term, so if you have x of tau delta of tau minus T naught d tau. Okay, basically whatever was in the previous line, I'm integrating from minus infinity to infinity. Now notice that you are integrating the Dirac delta which is occurring at t equal to T naught. It has got a scale factor x of T naught, and basically when you do this integral from minus infinity to infinity, the Dirac delta will give you a value of 1. So this comes out to be x of T naught. Okay. So when you integrate it at from minus infinity to infinity, you will get a constant. Otherwise, if you are just multiplying the function with the Dirac delta, then you will get a Dirac delta as the output scaled by the appropriate value, so that you will get the correct expression. So keep in mind that the property of the Dirac deltas is something that we will utilize in our representation, particularly in the process of sampling, and would like you to be familiar with these results, and we will explain more when we encounter these concepts. So we are ready to start today's session. We will look at, as always, some illustrations on the aspect of sampling. So let me start off by explaining the process, the framework. For this, I would like you to refer to Oppenheim and Schaefer, chapter 4, and this is a useful context in which we want to have. So what we are studying now is called periodic sampling or uniform sampling. Periodic sampling or uniform sampling, both refer to the same thing. That means there is all samples occur at multiples of Ts. So uniform sampling, and this sampling process is done by taking the continuous time signal xc of t and evaluating it at multiples of Ts. Okay, this becomes our sequence x of n, and n is equal to 0, plus minus 1, plus minus 2, and so on. So basically this is the process of sampling. And once again, let me just mention to you that continuous time xc of t, through the process of sampling, we go to the sequence x of n. This operation is what we call the C to D converter. And from here, we will move to x hat of n. And this happens through the quantizer. Now, the quantizer, we will touch upon this in the next session. But what I want you to keep in mind, when you talk about a quantizer, you are saying that the accuracy with which you can represent this number x of n is not infinite precision, but only a finite number of bits. So in terms of the quantizer, when we talk about it, we talk about how many bits are going to be used in representing this particular continuous time signal. What is the dynamic range of the quantizer? So from what is the maximum value in the positive side and the negative side? So we want to look at the dynamic range. What are the various quantization levels? Are they uniform, non-uniform? So basically this is another aspect that we will be looking at, quantization levels. And what sort of linearity are we able to maintain in the conversion from the continuous time signal to the discrete time signal? And invariably we will have to use a circuit called a sample and hold circuit. And we must know the characteristics of the sample and hold circuit. So all of this comes into play when we are doing the quantization. But for today, we will be focusing on the continuous time signal being converted to a discrete time signal. So the quantizer, we will take it up at a later point. So the important thing to note is that in the process of going from the continuous time to the discrete time signal, there is an intermediate signal that we will study. That intermediate signal is a function or a signal which is called xs of t. So we take xc of t and then multiply it by a sequence of Dirac deltas. So xs of t is a continuous time signal which consists of Dirac deltas which are scaled. So this intermediate signal is very important for us to be able to eventually get to the continuous time signal. Okay, so we will focus on this. Let me just give you a quick mention of what xs of t is. This is a continuous time signal. Okay, it consists of a number of Dirac deltas with a sequence of Dirac delta functions. Dirac delta functions which are these Dirac delta functions, you will find that they are scaled because they are multiplying the continuous time signal, and they are shifted in time because the Dirac deltas all occur with the spacing of Ts. So scaled and shifted in time. Okay, scaled in amplitude, and we will explain this in a little bit more, in more detail. Now, why are we doing this? This is a way by which we can use the mathematical framework to explain the sampling process. Okay, so this is the way by which we can. So we may not do this exactly in hardware, but this is a mathematical framework which helps us to understand and helps us to fully visualize what is happening with the sampling process. But before we get to the theory, we should also have a good understanding of what the sampling process is and what are some of the key elements. So let us look at some examples which I would like you to take a look.